This program is brought to you by Stanford University. Please visit us at stanford.edu.
Here's space. Let's concentrate on space. No energy around. We can take space-time to be flat, but in particular, if space-time is flat, it's just ordinary Minkowski space, we can certainly imagine that space is flat by slicing through it in a flat way. But now let's put a particle into it. If we put a particle into it, particles have energy, and the right-hand side is no longer zero. At the point where the particle is, and only at the point where the particle is, there's curvature. Can you think of a geometry which has the property that it is flat everywhere except at a point? A cone. Yes. So the solution of the problem of general relativity of a point mass is that space is a cone, and of course there's also time. Space-time, if we want to think about it, we could think about it this way. Time goes up, and space, instead of being just flat, it is just flat, but right where the particle is, there's a conical deficit, a deficit angle, just like when we make a cone by cutting out with a scissor a piece of deficit angle. Okay, now, how big would you think the deficit angle is? Well, if there's no particle, then there's no deficit angle. What if there's a particle of mass m? What would you think? Proportional to m. Exactly so. That's exactly right. The deficit angle here is proportional to m. But the deficit, and in fact, it doesn't have to be a particle. It could be any distribution of energy that's bounded. It won't be exactly a cone, but outside the region where that energy is, it'll have the same geometry as a cone. So it might be a cone with a sort of rounded surface to it, but that's not so important. All right, now, then comes the question, how big does this mass have to be before the deficit angle is 360 degrees? There's nothing left when the deficit angle is 360 degrees. The space has essentially disappeared. What has happened is it's closed up into a, thank you, Michael. The cone has gotten narrower and narrower. The deficit angle eventually goes to a point where there's no cone left. At first it started as a big flat cone when the particle at the center was light. As the particle got heavier and heavier, the cone shrunk until there was no cone left. There's a maximum amount of mass that you can put into 3 dimensions before it closes up and just closes up and disappears. How big is that mass? Not very big, the Planck mass. So we are not going, it's the only mass of the problem. So, well, no, it's a dust grain. Right. So at most you could have, in the way of life in 3 dimensions, you could have a single microorganism. Not much room to develop an intelligence, and so forth and so on. So space of 2 dimensions is clearly ruled out. Space of 1 dimension turns out to be even worse. Gravity in 1 dimension space, 1 dimension of time, is so sick that it's not even worth thinking about. 3 dimensions, 3 space dimensions, 1 time dimension, gravity behaves in the usual way. What happens when you go to 4 dimensions? Well, it's not just gravity. It's gravity and also electromagnetism, which is sick. Now, first of all, I'll tell you in what way gravity is. Gravity is not so much sick in 4 dimensions. When I speak about dimensions, I'm speaking about spatial dimensions. In 4 dimensions, 4 plus 1 dimensions, gravity is reasonably healthy, but there are some dynamical features to it which make it awkward. The solar system would not be stable. The solar system would be very chaotic. This is just a particular fact about dimensions higher than 3 that the Newtonian force law, or the force law that would derive out of Einstein's equations, has bad instabilities, and so the solar system would be very chaotic, and the result of that is it probably wouldn't take very long before the planet got ejected out of orbit. But things are much worse than that. That's not the worst thing. That's by no means the worst thing. And yeah.
Do you still get the Newtonian gravitation 1 over r squared?
No, you don't get 1 over r squared. That's why it's funny. You get 1 over r cubed. As you go up in dimensions, it goes from 1 over r squared to 1 over r cubed to 1 over r to the 4th. Now, the real problem has to do with atoms. Electrons are little solar systems, and it's not just gravity which goes from 1 over r squared to 1 over r cubed and so forth. Electromagnetism also does. It's governed by the same kind of force law. Coulomb's law and Newton's law have the same form, and that's true in every dimension. So what happens as you go in higher dimensions is the attractive force of gravity becomes stronger and stronger at small distances. 1 over r cubed, let's compare 1 over r cubed with 1 over r squared. 1 over r squared, excuse me. This is the force law when there are 4 space dimensions. This is the force law when there are 3 space dimensions. Well, if I were to just, I'm afraid we're going to run out of ink tonight. 1 over r squared, let's first plot 1 over r squared. Now, is 1 over r squared bigger, is 1 over r cubed bigger or smaller than 1 over r squared? It's not well defined. You have to tell me where. At r equals 1, they're exactly the same. At r bigger than 1, r squared is, of course, the larger. Yes. So 1 over r cubed is smaller, but at small r, 1 over r cubed is bigger. So one can expect then that the force law holding atoms together will be weaker at large distances, but much smaller at small distances. The effect would first of all be the long-distance Coulomb force, which holds the outer electrons in place, would be much weaker, and there would not be valence electrons and so forth. They would just fly off. They would fly off. On the other hand, the inner electrons would be pulled in much more tightly. In fact, in 4 space dimensions, the Coulomb law, when combined with quantum mechanics, would pull the electrons right into the nucleus. So there wouldn't be atoms. Without atoms, there is no chemistry. It only gets worse in 5 dimensions and 6 dimensions and so forth. So we don't know really why 4 dimensions. What we do know is we couldn't be sitting here if the number of dimensions was higher. Yeah.
So is the number of dimensions that the nuclear forces are seeing larger?
Say again?
So is the number of dimensions in which the nuclear forces is larger, and therefore they exhibit 1 over r cubed or r to the 4th? Kind of
I didn't understand. You asked me something about the nuclear force. Right.
or strong force.
They would also be stronger at small distances and would probably do real damage to the theory of quarks and leptons, quarks in particular. Theory of quarks would not bind together properly into protons and neutrons. I've concentrated on atoms, but much of what I said you could also say about the forces that held quarks together and so forth. So it would be bad. And besides, it's not entirely clear that topologically, that sex is possible in higher dimensions. This is important.
The conversation gets longer and longer. Can you say anything about 3 spatial dimensions and 2 time dimensions?
No. That just boggles the mind. I don't know how to think about a world with more than 1 time dimension. That's no.
It seems like I have 3 time dimensions to match the 3 spatial dimensions.
Yeah.
By symmetry.
It's not clear, right. It really isn't clear how to think about what it would mean to have more than 1 time dimension. It's so confusing that, no, I have nothing to say about it right now. Okay, so 4 dimensions does seem to be special. As I said, not for deep mathematical reasons as far as we know, but there are certain features of basic physics which seem to work in 4 dimensions, which for one reason or another seem to be very thorny and problematic. Atoms, stability of the solar system, the fact that in 3 dimensions you can't have more than a Planck's worth of mass before you close the universe up into an infinitely narrow cone, so forth and so on. Any other question?
On the same vein, why does time deserve dimensional status?
Well, that I don't know what that means. It's a dimensional status. I mean, why do we call it a dimension?
Yeah.
Well, why not? Well, the real reason we call it a dimension is because of Einstein, whose special theory of relativity mixes space and time together with transformations that resemble mathematically rotations of space. In other words, there are transformations which mix space and time together. So it becomes natural to think of time as a dimension of a 4-dimensional space-time. There's no unique, in 4-dimension and space and time, there is no unique time axis perpendicular to a space axis. A moving reference frame as a time axis which points in some other direction. The corresponding space is also tilted. So there's no uniqueness to what the time axis is, and they get mixed up with each other, and it's quite profitable. The mathematical structure of the theory, the space and time come in fairly symmetrically.
Or as you pointed out, you can apply boost and change energy.
For example, and energy and momentum are time and space components of 4 vectors. So
Last week, I think you said you would show us where the cosmological constant went into the equation.
yeah.
That's part of the lecture you're planning? Or?
I actually hadn't, but I'll tell you right now. The question, the more interesting question, is what does the cosmological constant do? But first, let me tell you where it goes in the equations. Let's remember what's in the equations. On the left-hand side, we have something that involves geometry. I told you that the only tensors that we can make out of the gravitational field that have 2 indices. Remember, on the right-hand side, we're going to have the energy momentum tensor, 2 indices. The only simple tensors that can be constructed, or the simplest ones, are R mu nu. And whether I put the indices upstairs or downstairs doesn't matter. You can raise them, lower them, same thing. R mu nu, and minus some constant, whether it's minus or plus, we'll figure out later, G mu nu times R. Now, that's not quite right. The coefficient here is determined by requiring, well, we're going to put on the right-hand side T mu nu times a numerical constant, 8 pi times the Newton constant, but sometimes just called K, we expect and hope that energy momentum will be conserved. That means that the covariant derivative del mu of T mu nu, a kind of continuity equation for each component, momentum and energy, a separate continuity equation for each. And if that's true, then it had better be that the left-hand side also satisfies the same thing. Incidentally, to make it satisfy the same thing, we'd have to put the indices upstairs, but that's no big deal. And what Einstein discovered is that very generally, no special assumptions about the geometry, if he put a 1/2 here, then in fact, the left-hand side satisfies, let's see, this tensor as it stands is called G mu nu, G for gravity, or if we put the indices upstairs, G mu nu, it automatically satisfies for any geometry this identity. So that fixed the form of Einstein's equations with one ambiguity. There is one more tensor that you can form out of the metric which has the property, which has this property. This property is called covariant conservation. There's one more tensor that you can form, and that tensor is just the metric itself. The metric itself satisfies del mu G mu nu is equal to 0. It's equivalent to the statement, yes, that's correct. Why is that? The reason is because the all covariant derivatives of the metric tensor are 0. The metric tensor is the one tensor whose covariant derivatives are all 0. One way to see that is to go to a reference frame where the metric and all of its derivatives are equal to 0. We talked about such a frame. You can always choose coordinates where the metric is constant. The constant simply means its first derivatives are equal to 0. That means the Christoffel symbols are 0. If the metric has no derivatives and the Christoffel symbols are equal to 0, then the covariant derivative of the metric must be exactly equal to 0. The covariant derivative, all covariant derivatives of the metric are equal to 0, but in particular, the one which corresponds to this continuity equation, from here to here is just replacing little g by big G, it's also true. So that means there's one more thing that we could have added into the left-hand side here, plus some constant, any constant, lambda times G mu nu equals K T mu nu. What's that? Ooh, can't do that, can you? That's illegal. Right. That's the one ambiguity that Einstein discovered in his equations. Lambda is called the cosmological constant. It can be positive or negative. And we'll talk about it. What it actually corresponds to is a modification of the gravitational force law. And depending on the sign of lambda, it either adds an attraction or a repulsion. But it's an attraction or repulsion which is quite different than the Newtonian force law. It's a force which grows with distance. Instead of F equals 1 over r squared, it's F proportional to r. So we're going to talk about this later, but for the time being, it's just an ambiguity that was in Einstein's equations. The numerical value of lambda was known to be extremely small. Einstein and everybody else at the time, and for many, many years, thought that there must be a reason why this is not there. Nobody knew any reason for it. we know now that it is there with a very small coefficient. So this is called the cosmological constant, but for the most part, we're going to talk about the theory without cosmological constant, at least until we get to cosmology. The reason is that the cosmological constant is so small that the repulsive force that it creates is completely insignificant until you go out to distances which are cosmological, and until you go out to distances of tens of billions of light years, or billions of light years anyway. Yeah.
Would it be fair to say that the first equation, you start out by getting there by, some kind of tensor analysis of
This,
ways
here.
that might work? Then you must have to verify that. with some
This
kind of-
equation.
But you have to verify with experiments. I mean, that equation is not derived from first principles, is it?
This equation. Yes, this equation.
I'm talking about Einstein's equation.
Oh, this equation here. No, this is, all right, so let's go back a step. What Einstein was looking to do was to convert to tensor notation equations which in certain limits reproduced Newton's equations. It was a guess. Not that he had to reproduce Newton's equations in those limits, but that the right thing to do was to look for tensor equations, equations which would be true in any reference frame. The right-hand side here, for very, very slowly moving masses and weak gravitational fields, the right-hand side here is only significant when you have two indices 0, 0, 0 component, and then it becomes the energy density. The energy density on the right-hand side here, with this kappa. On the left-hand side, if you make the approximation that the metric is not very distorted from the flat space form, that it's close to the flat space form, and if you assume that the metric of a static object like the sun or something like that is static and doesn't change with time, then it's not hard to show that R00, what we're going to do is take the 0, 0 component of this equation. 0, 0, that means energy density on the right-hand side, and on the left-hand side, you work it out, but what you find out is that it's proportional to some second derivative with respect to x, m squared, space derivatives, purely space derivatives. In fact, we can write it in the form of del squared. It's got two derivatives in it. Of what? Of g naught naught. Now, I'm probably missing a factor of 2. I always get the factor of 2 confused. But if you remember, g naught naught was very closely related to the Newtonian potential. So this just became the equation, the Laplace equation, or whatever it's called, the Poisson equation, connecting the gravitational potential with rho. Did he derive this equation from first principles? No, he used a correspondence with Newtonian gravity. He made an assumption, the assumption being that the equations should have the same form in every reference frame. This was a big deal for Einstein. He felt deep in his heart that that equations should have the same form in every reference frame. You can't prove that. You can postulate it and see what you get. What you got was a tensor version of Newtonian mechanics, which would be true, if it were true in any frame, would be true in every frame. Now, it has, of course, empirical consequences. It's not exactly Newton's theory. It differs in various contexts. Its empirical consequences are different when things move fast or when matter or the material that's gravitating is so dense that it creates very powerful gravitational fields. Then it doesn't, Newton and Einstein don't really agree, and there Einstein wins empirically. So, right, you're perfectly right. This didn't this wasn't entirely just out of pure air. It came from looking for a particular realization of tensor version of Newton's equations. Now, before we study particular solutions of these equations, in particular the Schwarzschild solution, which is a black hole, before we enter into that, which I want to at least start to do tonight, I want to talk about the way physicists today think about the equivalence principle. Remember I showed you how Einstein thought about light falling. He thought about light falling by saying light in an ordinary reference frame, an inertial reference frame, moves in straight lines. If it moves in straight lines in an inertial frame, then in an accelerated frame, remember the elevator, there's the elevator. If it's accelerated upward, then from inside the accelerator, the light beam will seem to fall. He wanted to generalize that idea. That was a very simple idea, good enough for a simple version of elevator physics, but he wanted to do much better than that. What he realized is that the equivalence principle, what it said was, first of all, that physics should be the same in all reference frames. That the equation should be the same in all reference frames. But beyond that, he said, if you choose coordinates, now you can only do this locally, remember, you can't do this over the whole space, but if locally you choose coordinates in which the metric is just equal to the metric of special relativity. In other words, if you work with coordinates which locally, for which g mu nu is equal to eta mu nu, which is just equal to 1 minus 1 minus 1 minus 1, then in the vicinity of that point, the equations of physics should have the same form that they have in special relativity. So here's what he said. He said, if we know equations in special relativity, we can take those equations and try to make tensor equations out of them so that they will be true in any coordinate system. And once we have those equations in tensor form, then we can just take them over as they are into situations where space might really be curved. So what he was in effect saying is that on small enough volumes, small enough regions of space-time where curvature can't be detected, same like the surface of the Earth. A small patch of the surface of the Earth, you can't detect curvature. The motion of balls rolling on the surface of the Earth and so forth, for small patches, looks exactly like the motion of balls moving on a flat plane. That's what Einstein said. He said in space-time, if you study regions of space-time which are small enough so that curvature is not important, then the equations should have the same form that they have in special relativity. Let's take the equations from special relativity and do something to them so that they become tensor equations, and then we'll know what equations should be in general relativity. Just the same tensor equations. Let me give you an example. We've already done that with the motion of particles. What's the law of motion of a particle in an inertial reference frame? Well, let's suppose there are no forces acting on the particle. Right. No electric, no magnetic forces, just a force-free particle. It moves in a straight line with a constant velocity. That's the same thing as saying it moves in a straight line through space-time. Moves in a straight line through space-time. Einstein's generalization of that is that particles move on the straightest possible lines. Lines which locally look like they're going straight ahead, and that meant geodesics. He didn't have to invent a force law. He simply said, I'll take what I know from particles moving without any gravitational forces on them, that they move in perfectly straight lines, and I will say locally along the trajectory, as long as curvature is not important, they'll just move straight ahead exactly as if they were in flat space. And that became his principle: particles move on geodesics. From that, we were able to deduce the equation of motion for particles, the geodesic equation of motion, and relate it to Newton's equation for the motion of a particle in a field of acceleration. All right, I want to go through another example and show you how it works. Wave motion. We could use Maxwell's equations, but Maxwell's equations are a little bit complicated. So let's take the wave motion of a simpler field than electric and magnetic fields, a scalar field. Last quarter, when we did a little bit of study of field theory, we talked about the structure in special relativity of a scalar wave equation. Was it last quarter? I think it was some number of quarters ago. Right. Maybe it was a half ago. Maybe it was a half ago. Maybe it was 3 quarters ago. I don't remember. But we did talk about wave equations in special relativity. Let's write down the wave equation in special relativity for a scalar field and then see what we can do to turn it into a general relativity equation. All right, so let's start with waves moving up and down one dimension. Waves moving up and down one dimension with the speed of light. All right, sometimes I'll use the speed of light equal to 1, sometimes I won't. For the moment, let's let the speed of light be general. Anybody remember what the equation of motion of a wave looks like, a wave equation for moving up and down a line? It's got a field. Let's call the field phi. Just on a one-dimensional axis to begin with. Well, it has some derivatives of phi, time derivatives of phi and space derivatives of phi. And the form of the equation is that the second derivative of phi with respect to time squared, this is the simplest possible wave equation, that is equal to the second derivative of phi with respect to, let's call the space coordinate x. No, that's not quite right. If we put the speed of light in, let's see, I think we have to put c squared here, is that right? Yeah, c squared here. Then that describes waves, two kinds of waves, waves which can move to the left or waves which can move to the right. And the shape of the wave stays fixed. That describes waves which move sort of rigidly down the axis, preserving their shape either to the left or to the right. Those are the two kinds of waves. Of course, you can have superpositions of them. You can have one wave moving to the right, another wave moving to the left. And what will happen is they'll just pass right through each other. That's the wave equation in one spatial dimension. Now, supposing I want my wave to be moving not along the x-axis, but along the y-axis, what do? Well, I just substitute y for x. What if I want my wave moving in a general axis? What do I have to do to this wave equation to describe the general kind of wave that can propagate in 3 spatial dimensions? And the answer is simple. You just add d second phi by dy squared plus d second phi by dz squared. If I set c equal to 1, now let's set c equal to 1 so that we go back to our notation that we've become familiar with. We set that equal to 1. We can then write this in the form the second derivative of phi with respect to x mu. Watch what I'm going to do. X nu times eta mu nu equals 0. Let's see why that is. Remember what eta mu nu is. its time component is 1. That means, and of course this is contracted, summed over mu and nu. All right? Let's start with mu and nu equal to 0. In other words, the time component. Then what we'll get is the second derivative of phi with respect to t squared. X naught is the same as t. So eta naught naught, that's 1, times second derivative of phi with respect to t, with respect to t again, that's just second partial of phi with respect to t squared. Now, what about eta 1, 1? First of all, the off-diagonal terms are 0. Eta, just remind you what eta is. Eta is the matrix 1, minus 1, minus 1, minus 1. It has no off-diagonal elements, so there are no terms here in which, for example, contain a derivative with respect to x times a derivative with respect to y, or derivative sub t, time, no mixed ones. All right, now what about eta 1, 1? What is eta 1, 1? Eta 1, 1 is minus 1. So let's see what we have. From eta naught naught, we have second phi with respect to t squared. And now what about eta 1, 1? That's minus 1, and it becomes second partial of phi with respect to x1 squared. What about eta 2, 2? Same thing. Plus the third term. Well, that's just this. In particular, if I transpose this to the other side and set it equal to 0, we've written the wave equation in what looks like a nice tensor form. But is it a tensor form? It is not. We have not yet succeeded in making a tensor equation. We've succeeded in making a nice formula, but it's not a tensor equation. So let's see why. Let's see what this says more carefully. Do it in two pieces. First of all, eta mu nu is not a general tensor form, but we might just want to replace this by g mu nu. That we can do. All right, so g mu nu, we might put g mu nu here. That looks more tensorish, but it's still not a tensor equation, and the reason is because these are not covariant derivatives. Let's write it this way. We have g mu nu d phi by, let's start with dx nu. Now, I've obviously not written the thing that's up above, but let's multiply it by d by dx mu. Well, that's clearly not the same as the thing I've written here. Why? Because, first of all, g depends on position. So when I differentiate, I'll get one term with a derivative of g mu nu, and another term of just the type that I have here. So I haven't first of all, this is not necessarily a tensor equation, and second of all, it's not this. Okay? But before I differentiate it with respect to x mu, let's erase this for a moment, and let's forget g mu nu. Is this a tensor, d phi by dx nu? Yes. The derivative of a scalar is a vector. So the first step here is a good tensor. What happens if I multiply it by g mu nu? Is it still a tensor? Yeah, it's a tensor now with an upstairs index instead of a downstairs index. Now what happens if I differentiate? And what is it? It's a tensor, but it's a vector. In particular, a vector with one contravariant index. Now what happens if I try to differentiate it? D by dx mu. Is it a tensor now? No. What do I have to do to make it a tensor? Take the covariant derivative. Incidentally, I started with this equation here. I could have taken the d by dx mu outside. Remember, eta is a constant, a bunch of constants. You can differentiate eta or not differentiate eta. It doesn't make any difference. But this, as it stands, is not a tensor. Incidentally, how many, well, tensor or not, how many exposed indices does it have? 0. Mu combines with this mu, and nu combines with this nu. So if it were a tensor, which it is not, what kind of tensor would it be? A scalar. But this is not the right rule for making a scalar out of a vector. We have to replace this by covariant derivative. So we have to add to it plus gamma mu. Let's call this object here. This is a vector. Let's call it v mu. Yes, let's call it v mu. We're covariantly differentiating v mu with respect to x mu. And so that means we have to, let's see, we have to put another mu here, a nu, and a v nu, I believe, which is just, let's see if I've got it right. And v is d phi. I'm messing this up. Let's go back.
You want the partial on the first one and the gammas?
Yeah. That's right. We want partial on the first one, and then gamma mu. Yeah, v is the whole thing. So then I should put v mu, right? Gamma mu, no, let's see, I don't have it right. We have to put some indices into the gamma here. Gamma mu alpha alpha. I think I have it right now. Yeah. The derivative with respect to x mu gets replaced by a gamma mu. The index mu is upstairs here, and alpha and a v alpha here. But then v alpha is what? It is g alpha beta d phi by dx beta. That's the covariant derivative. We could write this in a very simple form. Del mu, covariant derivative of g mu nu d phi by dx nu. That's what it is. But to work out what the covariant derivative is means there's some Christoffel symbols. This is a more complicated equation than the equation that we started with, but it's a tensor equation. This is the wave equation in curved coordinates. In fact, it's a wave equation in curved coordinates whether or not the space is flat. It's a tensor equation. If it's true in one frame of reference, it's true in every frame of reference. And this, yeah.
Is it 0?
Yeah, it's equal to 0. So all Einstein did was he took the standard wave equation, Maxwell's equations, rewrote them in curvilinear coordinates, and then said, I'm going to insist that I rewrite them in a form in which they have a tensor form so that if they're true in one coordinate system, they're true in every coordinate system. Right? And how do they do it? Basically, the same rule. Replace ordinary derivatives by covariant derivatives. That's all. Replace ordinary derivatives by covariant derivatives, and that will give you your equation. Now, the new equation is more complicated, and notice in the equation, the gravitational field appears. Remember what gamma was? gamma played the role of a kind of gravitational force. When it was applied to the motion of a particle, gamma had things like the derivatives of the Newtonian potential in it. So what appears over here is a kind of gravitational force, and the wave equation contains not only what you might have expected, namely some second derivatives of phi, but it contains another term, and that other term is actually the gravitational force on the wave field itself. So that's how ordinary simple waves would interact with a gravitational field. The effect of this, of course, is to bend waves. This is a function of position. The wave equation now has a form in which the various coefficients are position dependent. Do you know any situation in which a wave equation has position dependent coefficients of various kinds? Yeah, varying density, varying dielectric constant, and so forth. And what is the effect of varying density or dielectric constant? In particular, it can bend the wave. It can bend the wave. When light enters water non-perpendicularly, the wave is bent due to the variation with respect to space of a particular coefficient in the wave equation. Here there are various coefficients in the wave equation. These depend on position. And the effect is, among other things, to bend waves, change their frequency, do various things to them that wouldn't happen in empty space. Waves don't just propagate along in straight lines anymore. They bend, they refract, or whatever the right words are. Refract, is that the right word? Which is refract? Refract is what happens when water goes, right. Right. Okay, so this is what's called the equivalence principle. Namely, the way you derive the laws of physics in a gravitational field is to take the laws of physics without the gravitational field and just convert them to tensor form. That's all. And then the Christoffel symbols and the metric and so forth then determine how the gravitational field affects the motion of waves or whatever you have. All right, so here then,
Just
Yeah.
one technical question here, just make sure I understand that Christoffel symbol, the gamma has mu upstairs and downstairs, right? Mm-hmm. Gamma has mu upstairs and downstairs.
yeah, it has mu upstairs and downstairs. Let's see why.
I think I see why, I'm just making sure.
Yeah. Yeah, the gamma has mu upstairs and mu downstairs. And then an extra index alpha, which combines with V alpha. And then I just wrote that V alpha.
So at the heart of all this is Einstein's conviction that things ought to be independent of coordinates.
Yeah.
Therefore, what makes sense.
Right. And more than that, that locally in little patches in which are too small for the curvature to be felt, they should behave exactly as if there was no gravitational field. Right, so it's a little more than just what you said. And a little more is the content of the equivalence principle.
Quick question. Does covariant differentiation of a product have the satisfy the Leibniz rule?
Right.
So why, I mean, if you just write that in terms of covariant derivatives, the G mu nu goes outside, doesn't it?
Yes, it does.
Yeah.
So let's just write it in terms of covariant derivatives. You know, an obvious thing to write is that, first of all, that the phi by dx mu is just del mu phi for ordinary derivatives of a scalar. Okay? And then what we had was G mu nu del nu. That's basically what I wrote. The d mu phi, that was just ordinary derivative, multiply by g mu nu of x, and then take the covariant derivative of what's in here. But then, as you correctly point out, covariant derivatives satisfy the Leibniz rule being that a covariant derivative of A times B is equal to covariant derivative of A times B plus A times covariant derivative of B. All right, so the covariant derivative of G times this is just two terms. The first is G mu nu of X times del nu del mu of phi. And the second involves the covariant derivative of G mu nu. But what's the covariant derivative of G mu nu? Zero. So this is it. This is the form of the wave equation. But the reason I wrote it in a more complicated way is I wanted to make very explicit how the spatial variations of G mu nu and the Christoffel symbols enter into the equation and effectively make it almost as though the curvature of space-time was a kind of variable material that light was moving through. That's not quite true, but sort of like that. Causes light to bend, among other things. All right. Now, good. So that told Einstein how to figure out the effect of gravity on things that he already knew about. The next question is, how do the things that he knew about affect gravity? That's equivalent, in this context, it's equivalent to asking the question, supposing I have a scalar field that satisfies such an equation with such a property, what do I put on the right-hand side? The right-hand side is energy and momentum. Light has energy. Light has momentum. Scalar wave fields have energy and momentum. So if I wanted to make a nice little closed system of gravity interacting with a wave field, here I've told you how gravity affects the wave field. Now I have to tell you how the wave field affects gravity. Okay, so let's see if we can figure that out. What we're trying to do is tie up the ends. We have wave equations here for phi, but we still need to figure out what goes on the right-hand side if we want to figure out how the wave field affects gravity. All right, so that there are many, many ways to do this, some sophisticated, some not so sophisticated, and we're not going to be sophisticated tonight. We want an energy momentum tensor that's made up out of phi. Now let's begin by forgetting gravity altogether and just imagine special relativity. In other words, flat space-time. And let's see if we can figure out something about the energy momentum tensor of a wave field. No gravity yet, just ordinary flat space-time, special relativity. We have a field phi. And now we can go back to ordinary Cartesian coordinates, in other words, Minkowski coordinates, and write the wave equation the way that we had it before. It really can be written, well, we can write it as, what did we have before? Eta super mu nu d mu d nu phi equals 0, right? That was the wave equation written in a nice covariant notation, but in flat space. No Christoffel symbols, no varying metric, just eta mu nu. Can we guess what the energy momentum tensor for phi is? Well, first of all, it has to be a tensor. So it has to be a thing with two indices. What can we do to phi to create and give it some indices? To give an expression involving phi that would have some indices? Well, we can differentiate it. Okay. I'm interested in a thing with two indices, let's say t mu nu. So, what can I make? I can make things like d mu phi, d nu phi. That's something I can make. What else? I can add in eta mu nu. We're in flat space-time now. I can add in eta mu nu times, let's call it d sigma phi, d sigma phi. Anything else you can think of? Yeah. Yeah. Okay, why am I staying away from second order terms? In other words, you're asking why couldn't I have things with two derivatives, such as d mu, d nu phi? Right. Okay. One of the terms, I'm using something that I already know, that I did teach you previously. Let's see if you remember it. Anybody remember what the energy of a wave field is? Just the energy. What does the energy of a wave field have?
Density and velocity.
What's that?
Density and velocity or amplitude.
Amplitude?
Take a look at this expression. What does it do if phi changes sign? What happens to this expression if phi changes its sign? It changes sign, right? It changes sign. That means if I take a wave field, which, if this were in the energy, then a wave field which looks like this, which might have positive energy, and a wave field which looks like this would not have the same energy. A wave field which is in every respect identical, except the sign of phi was changed from phi to minus phi, would not have the same energy. One would have positive energy, one would have negative energy. So one might expect then that is forbidden. And it is forbidden. The energy should be something which doesn't change sign when you change phi to minus phi. It's like a harmonic oscillator. Wave fields are very much like harmonic oscillators. Harmonic oscillators have coordinates x. The kinetic energy is x dot squared. The potential energy is x squared. If x changes sign, nothing happens to the energy. The energy is positive whether you pull the spring out to the right or whether you pull the spring out to the left. The same is true of a violin string. A violin string is a good example of a wave. Would you expect a wave which looked like this to have opposite energy from a wave which looks like this? No, you wouldn't. In fact, they can go into each other. They can vibrate into each other. And so one expects on general grounds that whatever the energy or in the energy momentum of a field phi is, that it should not change sign when you change the sign of phi. Now what happens to this expression if phi goes to minus phi? Nothing happens. It stays the same. Why? Because it's quadratic in phi. If phi changes sign, d mu phi changes sign, d nu phi changes sign, and the product doesn't change sign. So a term like this is not expected in the energy momentum tensor. But these two terms are perfectly good. we can add them together, and we can add them together with some unknown coefficient. Let's put an unknown coefficient there. What's a good number? What's a good letter for an unknown coefficient? C. Thank you. Good. Now what I want to do is I want to figure out if there's any value of C which will ensure that the continuity equation is satisfied. The continuity equation is d super mu T mu nu is equal to 0. Now this is a funny looking expression, derivative. You know what d sub mu means, right? That means derivative with respect to x mu. And it's got a covariant index downstairs, all right? D by dx mu. What does a differential sign like this mean with an upstairs index? You just raise the index. What do you use for the metric to raise the index? Eta mu nu. So this is a perfectly well-defined symbol with an upstairs mu there. It just means d super mu equals eta mu nu d sub little nu. The upstairs derivatives and the downstairs derivatives are the same thing except for some sign changes here and there. All right, so this is the continuity equation, or the conservation of energy momentum in special relativity. You can push the indices upstairs and downstairs. I used to write it, previously I wrote it this way, but it's the same thing. Indices can be moved upstairs and downstairs at will. And here's my continuity equation. We can also write this equation in neater form. We can just write eta mu nu on d nu just turns this into d mu phi. One downstairs d mu, one upstairs d mu. That's what the eta mu nu does. So here's what we have going for us. Phi satisfies that equation. And we want to find out if there's a linear combination of these two which is conserved. If there is, it will give us a candidate for the energy momentum tensor. In fact, it's unique. Okay, so let's just try it out. Let's differentiate this super mu, T mu nu. What do I get? Apply it to the right-hand side here. That gives me d mu d nu phi d nu phi That's the first piece, first term over here. All right, now, this is a product. Leibniz's rule can be applied. What do I get? I get d mu phi times d nu phi. That's one term. And what's the other term? The other term is plus d mu phi d nu phi. That's when the d mu here hits the second term. Well, what is this piece over here? That's zero. That's the wave equation. So let's get rid of it. Okay, now we still have this term over here. We still have to hit it with d mu. D mu, constant c, eta mu nu, d sigma phi. What is that going to have? Well, d super mu, eta mu nu, what is that? That's just d sub nu. D sub nu. What's it going to have? It's going to have a term with a d sigma phi, and then a term with a mixed derivative d nu d sigma phi. There'll be two of them. Can you see why there are two of them? One from hitting here and one from hitting here. They're both the same. You can juggle these indices upstairs and downstairs. It doesn't cost anything. So there are two terms, each of which have the form d nu d sigma phi times d sigma phi. Okay, but this term is of exactly the same form as this. A derivative of phi, and then, yeah, if I replace, let's see, if we replace sigma by mu, they're exactly the same thing. But we get two of these terms. We get two of these terms, and that means I want the factor of 2 someplace. I want the, let's see, what are we doing? Yeah, the question, I know I dropped it, but where did I drop it? I think we want c equals a half. I think we want c equals a half. With c equal a half, just go through this, go through it yourself. With c equal a half, this becomes an identity that this is equal to 0. That's an identity for all phi. Oh, for all phi which satisfy the wave equation. I used the wave equation. When I differentiated this term, there was one term which was d mu phi. That was the wave equation. Then there was another term, and it canceled this. It canceled the two terms from here. That's why I had to put a half here. All right, go through that. It's a little exercise, not very hard. If phi satisfies the wave equation, then this object over here satisfies the continuity equation. Let's see. Do I want a minus sign? Minus sign. Let's compute, now that we have it, and it's unique. There was no ambiguity. It's quite unique. Let's just see if we can recognize what the energy density is. Which term is the energy density? 0, 0. Does it matter whether they're upstairs or downstairs? It doesn't. It doesn't. When you pull an upstairs index downstairs, if it's a time index, it doesn't change sign. If it's a space index, it does change sign. But if we pull 2 time indices downstairs, then certainly nothing happens to it. So the energy density is either T naught naught or T sub naught naught, same thing. And let's see what we get. All right, we have mu and nu both being time. So what is this? I'm now going to use the notation x naught equals t, time. So what is this term over here? Just the square of the time derivative of phi. Not acceleration. No, it's just the square of the time derivative of phi. Let's just call it phi dot squared. Phi dot squared, this is the energy momentum density. Sorry, it's the density of energy. The density of energy. Phi dot squared, that's the first thing here. Dot meaning derivative with respect to time. And then minus 1/2. And let's see what we have. We have eta mu nu. So we're interested in the time component of it. What is eta naught naught? 1. So we just leave that alone. And then we have phi dot squared. Why phi dot squared? If sigma, the sigma is the same as the sigma in the summed over. If sigma is time, then raising and lowering doesn't do anything. Raising and lowering a time index doesn't change its sign. Raising and lowering a space index does change its sign. So we have phi dot times phi dot, but then we also have the space derivatives of phi here. This could be x. Then we would have derivative of phi with respect to x squared, but with a plus sign or a minus sign? Minus sign, because 8011, sorry, because pulling an index up and down changes its sign. And then same thing with derivative of phi with respect to y squared minus derivative of phi with respect to z squared. Sorry, derivative of phi with respect to z squared. What do we get all together? We get phi dot squared minus a half phi dot squared. That's phi dot squared over 2. And then the minuses here and the minus here cancels each other, and we get plus the derivative of phi with respect to x squared plus the derivative of phi with respect to y squared plus the derivative of phi with respect to z squared, and I think I left out a factor of a half, multiplying each one of these, all times 1/2. What is this? This is the kinetic energy of the moving wave. If we thought of it as a violin string, it would be the kinetic energy of the violin string. And this is the energy, the potential energy in the violin string, the stretching of the violin string away from its equilibrium when the violin string is straight. A straight violin string has no potential energy. When the violin string has a derivative, then it has potential energy. So this is in fact the correct expression for the energy density. We could also work out all the other components of the energy momentum tensor, but why bother? Here it is. This is it. You can go and figure out all of its components. There is one ambiguity. The one ambiguity is the overall coefficient in front of it. I could put a 10 in front of it or 100 in front of it, and it would still satisfy the continuity equation. Where is it? It would still satisfy the continuity equation. So there is an ambiguity. But that ambiguity can, and it is really there, it's ambiguous, but you can always absorb it into the definition of phi. Supposing I decided that the energy momentum tensor should be 100 times this. Well, then I could redefine phi by taking phi times 10 and calling it something new. And then the new field would have an energy momentum tensor which looked exactly like this. So there's a matter of convention. There's a bit of a matter of convention about the definition of the field phi. It is always defined so that the energy doesn't have a factor of 100 or a factor of 7. It's defined in such a way that the coefficient there is 1. Once you know it, you can put it into the right-hand side of the equations here. All right, so you take this now, bodily, bring it over to here, and it becomes the right-hand side which tells gravity how to respond to the energy and momentum in the wave field. Yeah?
Maybe it's a real naive question, but I've read long ago that pressure has something to do with
Yes.
general relativity.
Okay. Pressure pressure is simply defined in terms of the energy momentum tensor.
Okay.
Right. Okay, I'll tell you what. Pressure is a well-defined thing when a gas or whatever it happens to be is isotropic. If it's not isotropic means you can't, the molecules are moving as much this way as they are this way as they are this way when it's isotropic. if it's not isotropic, then there are different components of pressure in the various axes, and you have to think about something a little more complicated than pressure. When a gas or a material or whatever it happens to be is isotropic, then the pressure is a well-defined thing, the same in every direction. And when the gas is isotropic, it means that the energy momentum tensor, it has a T naught naught here, that's the energy density, but then it has nothing in the off diagonals. The off diagonals would render it not isotropic, and the only elements it has are on the diagonal, and those are called the pressure. Or are they minus the pressure? I think they're minus the pressure. Oh, the pressure or or 1/3 the pressure. No, they're the pressure. Right. So the pressure is just defined in terms of the energy momentum tensor.
Would shear force be an example of something off diagonal?
Yeah, yeah. A shear force would be, right. A shear force, a shear stress would be a non-diagonal component, but it would be symmetric. Right. So you can see then that even in isotropic situations, the pressure, as well as the energy density, really does enter into Einstein's equations. Now, when all the C's meaning the speeds of light, not the C over there, when the speeds of light are put into the equations, the energy density is much, much larger than the pressure. Why? Because energy density has C squared in front of it. So typically, unless you're in some situation where there are things moving near the speed of light, the energy densities are usually much larger than the pressure densities. Now, for a box of photons, where everything is moving with the speed of light, pressures and energies can be of the same order of magnitude. But in any case, yes, pressure enters into Einstein's equations, as well as shear forces. As well as, what is a shear force? A shear force is if you have a block of material and you try to shear it, you try to push one edge of it one way and the other edge of it the other way, that creates a kind of stress. That stress also enters into here. It's non-diagonal elements of T mu nu. So yeah. All right, so in fact, that's one of the things that Einstein discovered, that energy, momentum, and stress and pressure are all parts of the source of the gravitational field. They're all source of the gravitational field.
Is it beyond more than it takes a certain amount of energy to put, let's say, pressure into volume, and you could just call that equal to a mass?
No, it's more than that. It is more than that.
Because it's off diagonal.
Yeah, for example. Or for example, if these coefficients were not all equal to each other, different pressures in different directions, they might add up to a given amount of energy, but they would make the gravitational field do things which were different than if they are equal to each other. Right. So that's the basic idea of the equivalence principle. And, like John Wheeler said, well, I'll just paraphrase what he said. Energy and momentum tell the gravitational field how to bend, and the gravitational field, well, let's write it correctly now. Del mu, which has all kinds of Christoffel symbols and other things. The gravitational field tells the wave field how to propagate. That's how to propagate through space, through the curvature of space. And how does it do it? It does it by Christoffel symbols and metrics appearing within the equations here. Okay, any questions up till now? Yeah.
I think I see how you get an energy momentum tensor from a potential, from a stress,
From
fluid
phi.
motion, from fluid motion,
Oh.
from motion of charges.
how do you get an energy momentum tensor from mass sitting somewhere else?
From mass.
From a blob of mass over here, how do I know what the energy momentum tensor is? Einstein's equation exists at every point in space, right?
Right.
It's a point equation.
Right, but some energy over here creates an energy over here. It doesn't create an energy over here.
I have a mass here, and mass is equivalent to energy.
No.
So how do I calculate all 16 terms of the stress energy of the energy momentum tensor somewhere else?
There's zero. If there's energy over here and only over here, yeah, that's the energy. Then the then the energy momentum tensor is non-zero where the mass is.
So space can't be curved.
No, wait. That's two different things. Let's go back a step. Let's go back to Newton. Or not Newton, but Newton à la Laplace and Poisson. Newton à la Laplace and Poisson is del squared phi equals 4 pi g rho? 4 pi g rho. Same equation as here, at least in the appropriate approximations. Del squared phi is r naught naught, or something like that. All right. Now, supposing there's some mass someplace over here. That's where rho is. There's no rho over here, there's no rho over here, there's no rho over here. But does that mean that there is no phi over here? No. When you solve this equation, you'll find that there's phi all around this object over here. How do you see it? Well, one way to remember it is to use Gauss's theorem to tell you that there's a gravitational field. You use Gauss's theorem. What this equation is telling you is not that phi is zero out here, but that certain combinations of its derivatives are zero out here. The fact that there's a source determines a phi, but it determines a phi in a way in which this particular expression vanishes outside. And in fact, what does it do? It leads to the 1 over r squared, or the 1 over r force law, 1 over r potential energy law. Same thing here. This may be zero all over space except at a few points, but the curvature will be distributed over space in general.
Question? If light has energy and momentum,
Yeah.
then it affects space curvature. Does that mean that light can affect the propagation of light so they interfere and don't obey superposition?
Yes. Very good question. Example. Two light rays crossing each other. What do you call lines which are like this? I forgot there's a word in elementary geometry. Skew. Two skew light rays going past each other. They don't intersect, but they would intersect if they, just going past each other. Each one causes a gravitational field which attracts the other one. So instead of just going, can I do this? Let's see. Let's try. They go. They attract each other. You know what I mean.
Haven't they measured to very high energy levels that photons do not interact with other photons?
Yes. Remember that Newton's constant is tiny. It is very, very hard in a laboratory to measure the gravitational interaction between two kilogram balls of iron. A photon or a light beam has very, very little energy and very, very little mass. Its energy divided by c squared is its mass, and remember, it may be true that E equals mc squared, but it's also true that m equals E over c squared. So if you have some energy of an ordinary kind, ordinary magnitude, the mass that it corresponds to is minute, very, very small. If you then say that the gravitational interaction between these two things is their effective, let's write out what it would be. It would be their effective masses, this is terrible. It would be their effective masses, m1, m2, times Newton's constant, divided by r squared. R squared might be the distance of closest approach of these two light waves. Now, what is m1? It's the energy divided by c squared. E of light beam 1 times E of light beam 2 divided by c to the fourth. C to the fourth. C is 3 times 10 to the 8th, 10 to the 17th, 10 to the minus 34 in the denominator. 10 to the minus 34, and 7 times 10 to the minus 11 in the numerator. That's about 10 to the minus 10, 10 to the minus 44. 10 to the minus 44 times the energy divided by r squared. So in practice, of course, the interaction between light waves is entirely, completely negligible. You never have enough energy. Yeah.
A question on, maybe a historical question on cosmological constant. What you read in the popular books is that Einstein was compelled to put that in there to keep the universe from collapsing,
Yeah.
As opposed to how you described it earlier, where it fits right in there. Can you elaborate on that, maybe?
Yeah. Okay. Well, we're at it. Let's talk about the Let's talk about the cosmological constant. Okay. So we modify the equations r mu nu minus 1/2 g mu nu r, and then we add to it plus some lambda times g mu nu, and we set that equal to t mu nu, or k times t mu nu, or whatever. One can ask, what is the Newtonian analog of this? And there is a Newtonian analog of it. The right-hand side, of course, is the usual 4 pi g times rho, as always. The left-hand side has del squared phi, and then in addition, it just has plus lambda. Now, where did I get that from? I got this by looking at the naught component of the equation. On the left-hand side, this whole object over here, its naught component, apart from a factor of 2 or something, is just del squared phi. Look at the naught component of this and assume that the gravitational fields are very weak. That means that g mu nu is close to the special relativity value. The naught component would be 1. So Newton's equations would get modified by an extra term. Okay? Now, this here represents, if I just had no lambda, then the equation is telling me how phi out here responds to the presence of a point mass. But let's ask a different question. Let's ask how phi responds to just a cosmological constant. What is phi like if there was a cosmological constant with a Newtonian? All right, can you find a solution of this equation? Del squared phi is equal to lambda? The sign of lambda I'll figure out later. Let's just let's be loose and sloppy with the sign equals lambda. I can find it.
Everywhere. Gravity everywhere pushing.
Say it again?
Depending on the sign of lambda, it's either false or
Right, right. But look at it from this point of view. It's equivalent to just having a uniform mass density. It's equivalent to just putting a uniform mass density spread all over space. Now, what's the solution of this equation? It's not phi equals 0. It's not phi equals a constant. For phi equals 0 or a constant, you would get 0 on the left-hand side. Yeah. What if I took the function x squared plus y squared plus z squared? What's its del squared? It's a number. 6, right? Differentiating x twice gives me 2, y twice gives me, so this would be 6. So I think I want to put a 1 over 6 lambda, and then del squared of this, if phi is equal to this, del squared of 1 over 6 lambda, x squared plus y squared plus z squared. Did I do that right? No, lambda over 6. Sorry, lambda over 6. That's dumb. Lambda over 6, x squared plus y squared plus z squared, that would be the solution of the equation with just a uniform lambda on the right-hand side. Now, what does that mean? Remember what phi is. It's the gravitational potential. What do you do with a potential? You differentiate it to find the force. So let's find the components of force, or strictly speaking, the acceleration of an object. Phi has been defined in such a way that its gradient is acceleration. All right? So here we are. We have a particle over here. Here's the origin of coordinates. What is the x component of force? The x component of force is the gradient of phi along the x-axis. Or maybe it's minus the gradient of phi along the x-axis. Derivative of phi with respect to x is equal to lambda over 6 times 2x, right? Or lambda x over 3. What does that say? That says that the x component of force is proportional to x. Pushing away, well, depending on the sign of lambda, and had I kept my sign straight, we would have gotten it right. It's telling me that there's a component of force along the radial direction. The x component of force is proportional to x. The y component of force is proportional to y. And so it corresponds to everything in the universe being pushed away from the center by a force proportional to the distance and also proportional to the cosmological constant. Now you might ask, wait a minute, is there a special center? The answer is no. A force law like this, where everything is being pushed away from everything else, if you sat at the center, you would see everything being pushed away. But if you sat on one of the particles that was being pushed away, you would also see the original origin being pushed away from you. So in fact, it's a force law which really doesn't have a center. It really just corresponds to everything. What it corresponds to is everything expanding, everything growing, and the separation between all objects accelerating outward. So that's the cosmological constant. And Newton should have discovered it. It shouldn't have taken Einstein. Newton should have discovered it. Well, of course, or maybe Laplace, or maybe Poisson, or whoever it was who invented this kind of equation here. They could have discovered it. It was a possible thing in the equations. They didn't. But Einstein realized that there was an ambiguity in the equations. And for a while, he entertained this. Now, notice, you can put it on the other side of the equation. Minus lambda g mu nu. And you can therefore think of it as part of the energy momentum tensor. It's a part of the energy momentum tensor which is there even if nothing else is there. And so sometimes the cosmological constant is a little bit schizophrenic. It doesn't know which side of the equation it wants to be on. You can think of it as being on the left side of the equation, in which case it's part of the geometry side of the equation. Or you can put it on the right-hand side of the equation, in which case you can think of it as vacuum energy, energy that's there when there's nothing else present. You can either think of it as a uniform distribution of mass, or negative mass, or positive, depending on the sign of things, which is pushing things out. in other words, a funny form of energy, or you can include it on the left-hand side as a funny piece in the geometry side of the equations. That's up to you.
It's there no matter if there's also mass there. So
Yeah.
inside a star.
Yeah. Yeah.
Star doesn't neutralize.
That's right. But its numerical value in the real world is extremely small. Why is it so? How do we know it's small? It doesn't have any influence on anything astronomically until the distance. Remember, it's a force which grows with distance. It only becomes measurable and detectable when the distance is out a billion light years, a couple of billion light years, then it becomes detectable. Yeah.
My understanding was that if it was zero, that, or put it another way, that he introduced it because if it wasn't present, then he wouldn't, then the universe wouldn't, that his equation didn't have a static solution.
That's right. That's right. That's right.
And
Yeah, but that there he did make a mistake. Here's what he said. He said, look, the universe has been sitting here for a long time. Why isn't everything crushing in? Why isn't gravity pulling all the stars together and stuff? There's got to be some compensating repulsive force. So he introduced the cosmological constant as a repulsion which would counteract the attraction due to gravity. And it was possible, using the two of them together, to create an equilibrium where the repulsive effect of the cosmological constant would cancel the attractive effect of gravity for just the right magnet. It required a very delicate cancellation. Cosmological constant had to be just right. But what he didn't realize was that it was an unstable equilibrium, that it was an unstable and not a stable equilibrium.
Sort of an armistice.
Well, it wasn't an armistice. It was a bad armistice because it had stability problems. It was like you discover a rock hovering above the earth somewheres. What do you conclude? You conclude there must be some additional force to gravity which is holding the rock from falling. So you invent a linear force which pushes the rock away, and there's some equilibrium point where the attraction of gravity and the repulsion of this new force creates an equilibrium. Now let's look at it for a minute. It's interesting. Gravity is attractive, right? Let's plot the potential energy. Let's imagine, here's what we're imagining. Here's the Earth, here's a rock. The rock is noticed, it's not hovering because of centrifugal force, it just hovers. There must be some repulsive force that's keeping it from falling toward the Earth. Let's suppose it's of this kind, of this cosmological constant kind, so that it has a force which is proportional to distance. Can everybody read that? Force proportional to distance? Okay. Let's plot the potential energy. First of all, there's the potential energy of the rock due to the lump, due to the Earth. What does that look like? Potential energy. Positive or negative? Negative. So it looks like this. Oops, like that. Now, supposing this is a repulsive force, then there's a potential energy associated with it. What does that potential energy look like? Not a straight line. The force is a straight line. The potential energy would be a parabola. But would be a parabola going up or a parabola going down? Not if it's a repulsive force. If it's a repulsive force, remember, things push toward lower energy. It would look like this. Now, supposing your rock was right over here, would it be in equilibrium? It would be in equilibrium. What if you gave it a little bit of a push this way? What if you gave it a little bit of a push that way? That's exactly the situation that Einstein created by balancing the cosmological constant against ordinary gravity. I don't know whether he noticed it or not. It may be that he didn't notice that it was unstable. It may have been that he noticed it was unstable and didn't care, or but he regarded it as his most foolish blunder. But of course, it was far from a blunder. There really is a cosmological constant. What was a blunder was the idea that it could be used to keep the universe in equilibrium. That was false. But the idea that there should and could be such a cosmological constant in the equations, that is certainly true. Yeah?
Suppose that the cosmological constant acted as an attractive force. Would that produce a specific origin?
No. It would still be the same, that there's no specific origin, but what it would do, it would enhance the effect of gravity on pulling things together, and it would just create a crunch.
Why wouldn't the forces all act to direct it toward a specific origin?
There is no specific origin, but we'll come to that. That's why we're going to be studying cosmology, so that we can understand the geometry of a world with such forces, but without a center. We'll come to that, but not tonight.
Is it possible that the entire universe could be spinning and centripetal force is causing things to fly apart?
No. First of all, we know experimentally that there's no axis of rotation, just observationally. But even if there was some rotational axis, when you go far enough out, the universe can't be rotating with any very significant angular velocity. Why? Imagine it had a fixed angular velocity. When you go out far enough, it will be exceeding the speed of light. So you couldn't have a global, uniform universe which was all in rotation. At best, you could have some small region in rotation, and of course you do. They're called galaxies. But the galaxy cannot act like an axis which drags everything else with it just because of the speed of light constraint. Unless, of course, the rotation is so small that even out at the edges of the visible universe, the velocity is still so small that it's well below the speed of light. But that would really be observationally extremely small, the angular frequency.
We'd be a unique place here, too, wouldn't we?
Okay.
We would be unique, wouldn't we, if the,
Yes.
that happened?
Yeah, then that would place us in the center.
Oh, good.
You like that? Self-centered?
Going back to the energy momentum tensor, can you talk about the consequences of the off-diagonal terms?
Yeah. I don't want to do that too much right now. They create shear forces, and they create, they're, for example, very instrumental in creating gravitational waves. Gravitational waves are kind of shear waves. We haven't talked about them very much. I'm not going to talk about them tonight, but yeah, they're extremely important in creating gravitational radiation. I'm not sure what to say about them. But for example, there's no difference, incidentally, between, here is two things which sound entirely different. Take a block of material and try to shear it. Right? Yeah, so here it is. We take a block of material and we push this edge this way and that edge that way, making sure, well, let's say we hold this edge down on the floor, glue it to the floor, and push the top. That creates some stress inside the block. Now here's something that sounds entirely different. Take the block, squeeze it this way, and stretch it this way. In fact, They're identical to each other except rotated by 45 degrees. It's not hard to convince yourself that, if you think about it a little bit, that a squeezing this way and a stretching this way is the same as a shear along a 45-degree axis. Right? So what this means is that off-diagonal elements are the same as having on-diagonal elements which are different from each other. For example, a positive and a negative on-diagonal element. In any case, we'll come back to that, shear and so forth. It is important. It does have all sorts of consequences, but it's not a good time for it now. It requires a little more explanation. Yeah.
Is there an intuitive solution of these equations that sort of describes a planet going around a sun that will give us a little bit of sense of, you know, the meaning of the different metrics and, you know, what would be some kind of helix in free space?
Well, okay. The easy thing to do is to work, and we're going to do it. It's not that easy. But the easier thing to do is to solve the equations of gravity when the right-hand side here is just a spherical mass, the sun. We can solve it. We can find the metric. We can calculate all the Christoffel symbols. And we can calculate the motion of a small planet traveling around the sun. Absolutely. The solution is called the Schwarzschild solution. And it's the solution of a radially symmetric mass outside the mass. That's what we're going to do. We're going to study that solution. And it is also the solution of a black hole. The problem of solving Einstein's equations for two masses, both of which are big enough to create a significant gravitational field, you don't want to know. I mean, that's a job for a supercomputer. Not for human equation solving. So, yeah.
It's kind of intrigued with the idea of energy momentum tensor for light being very large, and so that skew beams would light beams going past each other would skew around each other.
You do that much better than I do. What? You do that much better than I do. Do it again. Do it again.
Now you're on the spot.
But anyway, doesn't that sort of imply that you could indeed have a high enough energy light density so that a beam of light would go in a complete circle the way it does inside the Schwarzschild radius?
What I said was not that light has a big energy momentum tensor. I said it has a very small energy momentum tensor.
Yeah, but, okay, but...
Small because there are c-fourths in the denominator, or c-squares in the denominator.
But in principle, could you still have...
So you're asking the question...
A ring of light or something like that.
Bound to what, though?
Going in the ring, going in the circle.
For example, around the star.
Well, maybe.
A black hole made out of photons.
Yeah. You could certainly have a light wave going around the circular orbit around the black hole. The trouble is the circular orbit of a light ray is unstable. Again, it's an unstable orbit, so if you have a mass, a given mass, and you consider a circular orbit at a certain distance, then the velocity of that circular orbit is fixed by the distance, by the parameters of the mass and the distance. So, for example, the Earth's distance from the sun determines its velocity. As you come in closer to the star, or whatever it is, the velocity gets larger. If you have a real, genuine black hole, you can get in close enough to it, not so close that you're trapped, about 3 Schwarzschild radii away from it, where there's a closed orbit of a light ray. In other words, a closed orbit where the velocity is equal to the speed of light. So there's one particular orbital distance where a circular light ray, circular path, a light-like circular path can exist. The problem is, if it deviates just a little bit in toward, then it gets sucked in, and if it deviates a little bit outward, it goes out. So it's an unstable orbit. So there's an unstable orbit for a light ray outside a black hole.
What if you had two hypernovae?
One of a kind.
If you were there, would you just see on that circuit, you would just see a plane instead of the actual...
A plane? You mean like an airplane?
I mean, the surface of the star would look like a plane. If you were in that circular orbit.
If you were on that circular orbit?
Yeah.
Well, it would be a light. You don't...
Moving at the speed of light, I mean, you wouldn't see any curvature seeing. The star would just look like a different plane.
Well, I'm not sure that the light beams can see anything. I would have to think about what a very fast observer moving around on close to that light ray would see.
No, let's say you didn't have to go as fast as the light, but I'm saying you're just at that distance. Then what it would look like is that
if you're at that distance being supported and kept from falling into the black hole, you would just see in front of you a great big horizon. Big black
flat plane. The surface of the star would look like a flat plane.
Oh, no, well, not quite. Yeah, this orbit is not quite at the horizon. It's the horizon is it's 3/2 times the distance to the horizon, to be precise. But I'm not. Look, when we get to the geometry of black holes, you will understand a great deal about black holes that you don't understand now, and you'll understand just how foolish your questions have been up till now. That's my goal. Okay.
I got one.
Yeah.
The eigenvalues of the stress energy tensor have special significance.
Yeah. They do. For example, the sums of the space-like eigenvalues divided by 3 is the pressure. The time-like eigenvalue is related to the energy density in a frame of reference moving with the fluid, if it happens to be a fluid. If the eigenvalues of the space-like, it has 4 eigenvalues. 1 in the time-like direction, 3 in space-like directions. If the 3 space-like eigenvalues are all equal, it means that in some frame of reference, the fluid, let's think of it as a fluid, is isotropic. If they're different, it means that there are some shear forces or squeezing and stretching. So yes, they definitely do have meaning. I mean, they basically characterize the state of affairs. Yeah.
Question.
Yeah.
If you have an isolated mass in space, then do you adjust the Riemann tensor so that so the curvature is 0 at infinity?
Yes.
Then how do you do that with the cosmological constant?
You don't. No. Good. If you have a cosmological, excuse me, if you have a cosmological constant, then the geometry that's associated with it is not flat at infinity. It's what's called de Sitter space or anti-de Sitter space, and it's an entirely different kind of geometry. So the answer is, if there's a cosmological constant, you don't adjust the geometry so that the Riemann tensor is 0 far away. In fact, if you have a cosmological constant, yeah, okay, let's go back. Let's see. If we have a cosmological constant, then we can set this equal to lambda g mu nu. I may have changed the sign of lambda, but it doesn't matter. Okay, now let's contract this equation with g mu nu. This becomes r. This becomes minus 2r. And what does this become? 4 lambda, right? 4 lambda. So we find that minus r is equal to 4, or lambda is equal to, or r is equal to minus 4 lambda. In other words, even if there's no matter around, if all there is cosmological constant, then out to infinity, the curvature scalar is exactly given by the cosmological constant. If there is no matter around, and only this, then one would say that, that space and space-time are uniformly curved. Uniformly curved because the Riemann scalar is uniform everywhere, just given by the cosmological constant. So I forgot what the question was, but I think I answered it.
In all of this, are we assuming that the universe is infinite?
No? No?
So we could have a model of a finite universe, even with the cosmological constant in concept?
No. Now, yes, you can have a model of one. The question is, real honest physics, when everything is taken into account, what can you expect? That's debatable. But yes, you can have a closed universe with a cosmological constant.
Do we know enough now to understand what frame gravity is?
No, not yet. No, I think we need to... well, we need to... yeah, no, not yet.
Do we know enough to understand what it is, whether the universe is flat or not?
Space-time is flat or space is flat? Space-time is flat means it's just absolutely empty and there is no energy or momentum, because if there were, it just wouldn't be flat.
Not locally, but
At infinity. Yes, it just means that, yes, it means that the geometry or the metric can be taken to just go to eta mu nu, far away. That's all it means. And it would be exactly the situation whenever there are some concentrated masses that create gravitational fields that fall off far away. Then space-time is asymptotically flat, is the right terminology. Asymptotically flat just means that the components of the metric asymptotically tend to eta mu nu.
But it's not obvious that that's true because there's investigation.
You mean in the real world?
In the real world.
It's not true. It's most definitely not true.
Well, it's bound to be closer and closer and closer.
What's that?
Investigation has shown that it's very, very close to being true.
No, you're confusing the curvature of space with the curvature of space-time. Okay. That's why I asked you, do you mean space or space-time? Right. Yeah, we can... I don't know how much we're going to get into that this quarter and how much we'll save it for next quarter. But flat space and flat space-time are two quite different things. We will go through the Schwarzschild black hole and the Schwarzschild metric, and if I have time, a little bit about the expanding universe. But I think it will take a full 2 hours to navigate through the Schwarzschild metric. And really, that's kind of the goal. That's the real thing. So I don't want to stop before we do the Schwarzschild metric. Right. Okay, so next week next week, yeah.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.